Hello and welcome back. This will be the video notes for section 10.3, Solving Quadratics by Graphing. There is a PDF available if you'd like to print it out and follow along. In this section we'll talk about solving quadratics using a graph and determining the number of solutions using a graph. You should have a graphing calculator. Graphing these by hand is not a good idea. The solution of a quadratic has many different names. Remember that a quadratic kind of looks like this. Y equals 2x squared plus 5x minus 7. And we could call the quadratic, or the solution of the quadratic, a root because we have powers of 2 here, and one of the ways we solve powers of 2 is by taking square roots, so we got the name root. And another name for a solution is called the zeros, or zeros of the function, and the reason we call them that is we've tried to find the value of x that goes there that outputs a 0 for y, and that's why we call them zeros of the function. And the last one, which is x-intercept, that's what we're going to be looking at today. How many solutions does a quadratic have? Well, a quadratic can have 2 solutions, 1, or it could have no solution. If you want to know how many solutions there are by looking at the graph, you simply have to ask yourself, well, how many times does the graph cross the x-axis? Whatever the answer is to that question ends up being the number of solutions. Here's 3 examples. We look at graph number 1 here, and we say, well, how many times does it cross the x-axis? This is x. Well, it crosses twice. So this graph has 2 solutions. Call this one graph number 2. Well, how many times does that graph cross the x-axis? Well, it only touches 1 time, so that has 1 solution. And then on graph 3, how many times does it cross the x-axis? X is way down here. This graph curves down towards it, but then changes directions. So there are no solutions. Example 1. Go to our graphing calculator, and we input this, and the graph pops up this graph for us. And we can see that it crosses twice. It crosses at 1, and it crosses at 5. So we would say that x is equal to 1, and x is equal to 5. Well, what that means is if we were to put in place of x a 1, we'll go ahead and do that real quick, plus 5 equals 0. If we were to substitute those in, this side would equal 0. So we have a 1 squared minus 6 plus 5 equals 0. 1 plus 5 is 6. 6 take away 6 gives us 0. And if we tried it with the 5, we would have a 5 squared minus 6 times 5 plus 5 equals 0. 5 squared is 25 minus 30 plus 5 equals 0. Well, 25 plus 5 is 30, and 30 minus 30 equals 0. So you can see that they are the zeros, or the roots of the function. They're also the x-intercepts. Example 2, when you go to put these equations into your graphing calculator, you got to make sure that it's equal to 0. Right now it's equal to 3. So we have to rewrite that as x squared minus 2x minus 3 equals 0. And this is what you put into your graphing calculator. Well, we go ahead and take a look, and we have nice roots here. We have 2 of them. One of them is at -1, and the other one is at +3. So the solutions here are x equals -1 and +3. And we know if we put these in place of x, it will force a 0 out. We don't need to test them in this case because we can clearly see on the graph that that's where the zeros of the function are. The output, which is the y value, comes down here and meets it in the middle at 0. So anything along this line, this horizontal x line, has an output of 0. Example 3. Again, we cannot have this over here equal to -16, so we got to rewrite it as x squared minus 8x plus 16 equals 0. Put that in the calculator, and we can see that there's only one root here, one x-axis, or one x-intercept, and it looks like it's 4, 4, 0, but the x-coordinate is what I'm interested in, so x is equal to 4. And that only had one solution. It didn't cross more than once. And the reason being is this graph was created by a perfect square trinomial, which can be calculated into x minus 4 squared, which means we have x minus 4 times x minus 4 equals 0. And we can see we end up with a +4 for both of those answers. That's why we only have one solution. Example number 4, I got to move this 4 over, and I'm going to move it right in between here. So I have a negative x squared plus a 4x minus 5 equals 0. And we can see that the x-intercept on this graph is actually, or the x-axis is actually up here, and there is no x-intercept. Therefore, there's no value of x that will cause this equation to equal 0. Therefore, this has no solution. Example 5. We want to solve this one graphically. However, with the exception of the last example, all the other examples have nice integer roots that we could see on the graph. Oftentimes, that's not the case, where we have to start estimating. In this case, they want us to estimate to the nearest tenth. So what we're going to do is go to the graph and estimate to the nearest tenth. Now that's 1 decimal place. So here's our graph. We've got our x squared plus 4x plus 1. Now remember, we're looking for the roots, the x-intercepts, or the zeros of the function. So we're looking for an output that is close to 0. We can see we have one over here that's somewhere between -3 and -4, and one over here that's between 0 and -1. But it's actually closer to 0. So I'm going to zoom in on that one and get a little bit closer look. It looks like it's around 1, 2. It looks like it's pretty close to 0.3. So I'm going to put in there a negative 0.3 and see what the output is. Well, that's pretty close to 0, negative 0.11. That's really close. If I were to go to, let's say, negative 2.9, well, I have a number here that's actually closer. You can actually see this puts a dot on there for me. So it gets closer to 0. And if I wanted to, I could probably get even closer. However, since I'm rounding to the nearest tenth, negative 0.29 is going to round up to a negative 0.3 anyway. So I'm just going to leave it as that. Okay, go down to my next one. Let me go back over here and see what these numbers were again. Okay, this is between 3 and 4 negative. Here's a 3.5, 3.6, 3.7. Looks like it's really close to 0.3 or 3.7. So I'm going to put a negative 3.7. And oh, look at that. It ended up having the same output. So these 2 points were equivalent on the horizontal. My guess is that's probably going to be the closest. I could probably go out to 3.75. Yeah, I got a little bit closer. But since I'm rounding, I'm going to go back. Now, I'm not going to round that up to an 8, because if I go to 8, negative 3.8, you see I get further away than I was on the other side. So I'm going to put that back at negative 3.7. So to the nearest tenth, negative 3.7 is closer than negative 3.8. So these end up being my two solutions, negative 0.3 and negative 3.7.